Hello, this is Vinay. In this ICP5, we are going to use the data of CIFAR 10 that we are importing it from the CIFAR 10 library. We are using the same data for the image classification. And here the main thing is that we need to use the 4 hyperparameters that affects the output. So here the 4 hyperparameters are, we need to explain them, how we have used it, and what are all changes that have been affected with these 4 hyperparameters and the explanation. So first step is the successful executing the code, changing the 4 hyperparameters in the model, then validating the model on 5 new images, then providing the logical explanation, wiki report, and the explanation. So moving on to our code. So here the first step is the importing the libraries. So here we have imported the libraries such as NumPy, and for the building the layers, we have used the keras.layers for models, keras.models, and we have imported the sequential model because we are using the same model to build the layers. And we are importing the convolution 2D, max pooling 2D for the convolutions. And we are for plotting, we are using the matplotlib.plot. So after that, we are splitting off the data. So here splitting of data here, basically we are using the CIFAR10, which consists of 10 classes of data like aeroplane, tracks, horses, and many more automobiles. We have such kind of data in this. So we are splitting them into xtrain, ytrain, xtest, ytest. Xtrain consists of the 50,000 of images. Ytrain consists of the labels of the 50,000 of images. Xtest consists of 10,000 of images, and ytest has 10,000 of labels. So after that, we are displaying the shape. So we are using the xtrain.shape to display the shape of that. So here we can see that for the xtrain, we have 50,000 of images, 32 by 32 pixel and 3 classifiers. And for the xtest, we have 10,000 of images, 32 by 32 pixels and 3 classifiers. Similarly, we are printing the data for xtext. Then we are printing the data of ytest and yshape. So here we can see that we have 50,000 of the ytest and 10,000, sorry, 50,000 of test and 10,000 of test and labels. Then we are dividing the data in the range of 0 to 1, because we know that the pixels maximum are up to 255. So whatever the pixels we are dividing it by 255, so that the range of this xtrain and xtest will be reduced to 0 and 1. So once we run this, we can see that the range of each and every xtrain image is between the range of 0 and 1. So after that, we are doing the one hot encoding, and here we are using the np underscore utils to categorical, and we are converting the data to encoding the data of ytrain and ytest, and then we are printing the class number. So we have 10 classes as said. So then we are printing the ytest. Next, we are plotting the graphs for this FIR10. So here I am using the 25 images of 5 rows and 5 columns, where I have given the figure size as 10 cross 10. For the 25 images, I have done the subplot. Then I'm showing the xtrain images. So once we run this one, we can see that these are the images with 5 rows and 5 columns. Then we are building a model. Here basically here we are building the model without any data augmentation and without any dropouts. So here we can see that first we are going by 32 and 3 cross 3, where 3 is the kernel size and 3 is the strides. Then we are going for the activation filter. Here we are using the activation filter as ReLU. Then we are giving the padding as same. After that, we are building the same for that 264, 64, 128, 256, the number of filters. Then we are building the dense layer, and at the end we are using the activation function as the softmax, so which gives the highest probability. So then we are compiling the model, and here we are using the loss as a categorical underscore cross entropy, and optimizer we are using the Adam we are using because it has the high configurations. With the default parameters itself, it's enough. We will get the desired output. So this is the best of all the optimizers. So we are going with the optimizer, Adam optimizer, and metrics we are giving it as accuracy. Then we are printing the summary. So this is the summary. In this, we can see that total parameters on this one, trainable are this, and non-trainable we have 1088. Then we are training the model. So here we have used the epochs as 25, batch size as 128. So here, without any data augmentation and without any dropout, we are getting the accuracy. You can see once here we are, since we have used the epochs as 25, it's taking around 25 seconds to run each epoch. So we are not going to execute it now, just I'm going through it. So here we can see that we have the loss, accuracy, value loss, and value accuracy. After this, here 391 is that we have 50,000 of images divided by the batch size. We have in each epoch this many images are run. So after that, we are plotting the graph for the values that we have obtained in the model. We are plotting the graph for the loss as well as the accuracy. Here we have the training loss, training accuracy, testing accuracy. So here we are plotting the two graphs. First one is for the accuracy and accuracy of accuracy and value accuracy. And next we are plotting the graph for loss and the value loss. So once so here we can see that once we run this model, the accuracy is of 95 for the training, and for the testing it's of 75. Then here we can see the graph. So here by clearly observing this graph, we can see that this is an overfitting. We have a huge difference here. So in order to overcome this overfitting, we are going for the data augmentation and the dropouts, so such that the overfitting problem is reduced. Because I mean, by using the data augmentation, it's clearly mentions that we are going to increase the data size, so that in one image, for example, we can alter it to various sizes based upon our requirement, so that the overfitting problem can be overcome. So we are going to save the model. So here we are using dot save function, and next we are importing the model. Then we are building the data augmentation here. After that, now we are building the another layer. The difference is that here we are using the max dropout as well as the data augmentation in the layer. So here we are doing the same with the dropout of 0.2, such that 2% of the data will be ignored. After that, we are compiling the data where loss equal to categorical cross entropy and optimizer equal to add metrics equal to accuracy. I'm not running each and every code because I mean, for the epochs, it's taking too much of time. It's taking around 10 minutes for each layer. So we are not running it. So this is the summary of the model. Then here we can see that we are building the data augmentation here. So data gen is a variable that we are storing the values of this data augmentation. Image data generator is a function that we are using, and we are using the vertical flip. We can either use the horizontal flip as well, and the rotation range we have given as 15, and the white shift range as 0.1, and height shift range as 0.1. Then we are training the model. Here we have used the same epochs as 25 and batch size as 128, and we are training and testing the data. So once we run this, here last time it has took around 25 seconds. Here for each epoch it's taking 43 seconds. So it will take around 10 minutes, to run this. So once we have got the results, by using the history function, we are plotting the graph. By using the history function, we can get the values of the accuracy, value accuracy, loss, and value loss. Then we are plotting the two graphs similarly. So here we can see that the accuracy is 95 and 75. So in the graph, we can clearly see that the overfitting problem we were able to overcome. So there is no problem of the overfitting. Then we are saving the model, and then we are importing it. If you want to save it to a JSON, we can use this function .json .to_JSON to use it. Then here we are doing the prediction of an image that is not given in the training or testing of the data. So here we are basically importing a sunflower image that is from this part, and we are going to predict with our model. So here I have done the prediction with model and model 2. So here we can see that the image is more for this sunflower. It says that the image is mostly belongs to ours with a 23.20% confidence, and for this image, bird image, we can see that it says that it matches with the with this with the 20.2%. So why we have taken these 4 parameters when compared to other is that we have used the another uh, uh, we have used another code where we can see we have given the epochs as 10, batches as 64, and without any training or testing, we can see that the accuracy of this is 0.77, and this is 92, where we have that as 75 and 78, and we can see that. So we have gone for those 4 hyperparameters. So now I will go to the wiki report. So here are the 4 parameters that we have choose, which are the optimizer. We have choose it as an Adam, batches as 128, epoch as 2.5, and robot as 0.2. So here basically the Adam operator we have used because it has the best properties in handling the sparse gradients or noise problem, and it has also the best configuration. That means that with the default settings itself, we can able to optimize is the model when compared to the others like SDG, SM, SPROP, or ADA Delta, or ADA Grad, or ADA Max. So we are using, and here we are using the batch size as 128, because I mean when we have used it as this batch size 64, we got the less accuracy. So we are changing the batch size as well, and we are going for the 128. And for the epochs, first we have used for the 10 where we got the less accuracy. So we are increasing the epochs. We know that I mean if we increase the epochs, the runtime will be increased, but anyhow we need to get the proper accuracy of data, so we are going to increase the epoch and dropout. So here we are using the 0.2% of the dropout. So here I have given the screenshots for the another case, and this is the documentation. Thank you.